Hi guys, welcome to today's video on our graph series. In the last video, I promised to show you the adjacency matrix and the adjacency list of our undirected graph. So for node A, we can see that node A has the following adjacent nodes: node B, node D, and node E. So in the adjacency list, we can see that node A has an array containing these adjacent nodes, which are node B, D, and E. And in the adjacency matrix for node A, we can see that the adjacent nodes, node B is filled with 1, node D is filled with 1, and node E is 1 as well, and the other ones are 0. So the same thing is applicable to node B. We can see that node B has the following adjacent nodes: node A, node D, and node C. So under the adjacency matrix, we can see that node A is 1, node C is 1, node D is 1, and in the adjacency list, node B has an array that contains this node. The same thing goes for node C. Node C has node B and node D as its adjacent nodes. So under node C, for the adjacency matrix, we can see 1 under B and 1 under D. And in the adjacency list, we can see that it is an array that contains just these two nodes. For node D, we can see that node D has the following adjacent nodes: node E, node A, node B, and node C. So we can see it well represented in the adjacency list in this array. And then in the adjacency matrix, we can see that these adjacent nodes are filled with 1. So under column A, we see 1. Under column B, we see 1. Under column C, we see 1. Under column E, we see 1. And the last node is node E. So node E has node A and node D as its adjacent nodes. So under the node E, we can see that we have 1 under column A and 1 under column D. And in the adjacency list, we can see that it is an array that contains node A and node D. So if your answer is correct, congratulations! You are doing great. Keep it up. So today we will be learning how to traverse a graph. Graph traversal is the foundation of solving graph algorithm problems, because almost all graph problems require you to traverse a given graph to perform some computations on each of the nodes to find something. So in this video, we will learn how to traverse a graph using the breadth first search and the depth first search. In breadth first search, you use Q to iterate over the nodes present in a graph while keeping track of the visited node and the explored node as required. So using this, our undirected graph, we will keep track of the nodes we have inserted into the queue. A queue uses first in, first out principle. What this means is that the first person to stand on the queue is the first person that will be attended to. Just like we have it in real life scenarios, when you stand on a queue in a grocery shop, the first person on the queue will be the first person to get the attention of the cashier. So the same thing is applicable here. So we are going to use a queue to traverse this graph. Now, we are going to use color red to keep track of nodes that we have inserted into the queue, and we are going to use a yellow color to represent nodes that we are visiting or we have visited. And finally, we are going to use color blue to show nodes that we have explored. Now, a node is said to have been explored if all its adjacent nodes have at least been visited, right? So bear in mind that this is to explain the concept of breadth first search. So we can start with any node, right? Because this is a graph, there is no root node in a graph. So we can choose to start with any node. I choose to start with node A. So the first thing for us now is to enqueue node A. That's insert node A to the queue. And then we bring it out and we visit it. We visiting it means we'll perform the required computations on this node. Remember that we can only say we have traversed a graph if we have gone through all its nodes and we have performed the required computation on each of these nodes. So now that we are visiting node A, we will perform the required computations on node A, and afterwards we are going to insert all the adjacent nodes of node A into the queue. Adjacent nodes of node A are node B, node D, and node E. So we insert them into the queue, and then we do the same for the next node in the queue. So we are going to be using the first in, first out. The first node in the queue, we are going to bring it out, visit it, perform the computations on it. If it has adjacent nodes, we'll push them into the queue, and we will continually take nodes from the queue using the first in, first out principle and perform these computations on them. So now that we are done visiting node A and performing the computations on node A, the next thing is for us to pick the next node from the queue, which is node B. So now we are visiting node B, and we will do the same thing. We perform the required computations on node B, and then we push in the adjacent nodes of node B into the queue. So the adjacent nodes of node B are node A, node D, and node C. But as we can see, node A has been visited, node D has been inserted into the queue already, so we are left with only node C. So we insert only node C into the queue. After that, we take the next node from the queue, which is node D. And then we are now visiting node D. We perform the required computations on node D. And then the next thing is to insert the adjacent nodes of node D into the queue. But now we can see that the adjacent nodes of node D, which are node E, is already inserted into the queue. Node A has already been visited. Node B has already been visited, and node C has already been inserted into the queue. So we don't have anything to insert into the queue. So we move to the next node. We take node E. So now we are visiting node E. Node E has node A and node D as its adjacent node. And these two nodes have already been visited. So there is nothing to insert into the queue. But now we can observe that node A has already been completely explored because all its adjacent nodes have at least been visited. You can see that its adjacent nodes, node E, D, and B, are all visited. So at this point, we can say that our node A has been completely explored. Also, node E has been completely explored because its adjacent node, node A, has been explored, and node D has been visited. So we can say that node E has been completely explored as well. So moving on, we'll take the last node from the queue, which is node C. Now we are visiting node C. We'll perform the computations on node C, and the next thing is for us to insert the adjacent nodes of node C into the queue. But as we can see that the adjacent nodes of node C, which are node B and node D, have all been visited. So at this point, there's nothing to insert into the queue. And at this point, we can say that all the nodes have been explored because all their adjacent nodes have all been at least visited. And at this point, we can see that we have completely traversed our graph using the breadth-first search because we have performed all the required computations on each of the nodes. Now, this particular method is called breadth first because it traverses the entire graph level-wise. What do I mean by level-wise? So, in a graph, the node you start your traversal with is the level 1, right? And all other nodes that are directly connected to it are level 2, right? And all the nodes that are directly connected to all the nodes in level 2 are level 3, and the list goes on. Do you understand? So we can see here that we first performed the computations on node A, which is in level 1, and then we came over to level 2 and we performed the computation on all the nodes in level 2. So we are going deep. We are not going deep, I mean to say, we are just taking it level wise. We are finishing all the nodes in each level before going to the next level. Immediately we finished all the nodes in level 2, you see that we now performed the computation on the last level, level 3, which is node C. This is not the case with depth first search. In depth first search, you don't necessarily need to finish processing all the nodes in a particular level before moving to the next level. Let's look at depth first search in more detail. In depth first search, we can either use a stack or recursion to traverse the graph. If you are using stack, it follows almost the same principle as breadth first search, except that while in breadth first search, you use a queue, which requires you to explore nodes from the queue using first in, first out principle, while depth first search will require you to use stack instead, which uses last in, first out. In this video, I will be explaining the depth first search using the recursive method. Guys, getting comfortable with recursive function is hard. I have come to the conclusion that the only way to get really familiar with recursion is through practice. Guys, what did I say? Practice. Yes. So in this channel, whenever the opportunity arises, I will always choose a recursive method because I want to become comfortable with recursion too. Yes. So now, let me explain how depth first search works using a recursive function. A recursive function has 3 parts. The base case, which is the point of exit. This is the condition that the function meets and it returns. This part of the function is what keeps the function from calling itself forever. Another part of it is what I call the action part or section. In this section, you perform the actual computation, right? And then finally the recursive section. In recursive call section, you call this function on other nodes. For this particular example, our base case would be when a node has been visited. Our action would be to mark the current node as visited to show that we are currently visiting it, and also to print out the value of the node. In the recursive call section, we are going to call this function on all the adjacent nodes of that node using a for loop. Now, bear in mind that your base case must not necessarily be the first thing in your function. It can be anywhere depending on the results you want to see. So I'm going to move our base case into the recursive call section so that before we even call this function again on a node, we need to first check if it has been visited before. So if it has been visited before, we just continue. That means we skip calling this function on that node because it is no longer necessary. Now, a recursive function uses a call stack to keep track of the processing node. Once you call the function on a node, it adds that node to the call stack. And once the function call on that node finish processing, it leaves the call stack. Now, just like in breadth first search, we are going to use red to indicate nodes that we are just inserted into a call stack. Once this function is called on a node, that node gets added to the call stack. And once the function call on that node finish processing, that node leaves the call stack. Now, we are going to use yellow color to also indicate nodes that we have visited or currently visiting. And we are going to use blue color to show nodes that we have explored. Now, remember this is a graph and we can start traversing the graph from any node. I choose to start with node A. Calling this function on node A adds C to the call stack. And in the action section, we mark node A as visited to show that we are currently visiting node A. And then we print out the value of node A. In the recursive call section, we look through all the adjacent nodes of node A and call this function on each of them. The adjacent nodes of node A are node B, node D, and node E. So, taking the first node, in the next line of code, we check, have we visited node B before? No, we have not visited node B before, so we call this function on node B, and this adds it to the call stack. Now again, in the action section of this function call, we mark node B as visited to show that we are currently visiting node B, and then we print out the value of node B. In the recursive call section, we loop again to call this function on all the adjacent nodes of node B. The adjacent nodes of node B are node C, node D, and node A. Taking the first adjacent node of node B, which is node C, in the next line of code, we check, have we visited node C before? No, we have not. So we call this function on node C, and this adds node C to the call stack. Now again, in the action section, we mark node C as visited to show that we are currently visiting node C, and then print out the value of node C. In the recursive call section, we loop through the adjacent nodes of node C and call this function on each of them. The adjacent nodes of node C are node B and node D. Taking the first adjacent node, node B, in the next line of code, we check, have we visited node B before? Yes, we have visited node B before, therefore we continue. That means we go to the next adjacent node, which is node D. And again, we check, have we visited node D before? No, we have not visited node D before. So we call this function on node D, and then node D gets added to the call stack. In the action section of this function call on node D, we mark node D as visited to show that we are currently visiting it, and then we print out the value of node D, and then we move to the recursive call section. There again, we loop through all the adjacent nodes of node D, calling this function on each of them. The adjacent nodes of node D are node E, node A, node B, and node C. Taking the first node, node E, we check in the next line of code, have we visited node E before? No, we have not visited node E before. Therefore, we call this function on node E, and it gets added to the call stack. In the action section of this function call on node E, we mark node E as visited, we print out the value of node E, and then we move to the recursive section. And in the recursive section, we loop again over all the adjacent nodes of node E, calling this function on each of them, starting with the first node, which is node A. In the next line of code, we check, have we visited node A before? Of course, yes, we have visited node A before. Therefore, we continue. That means we go to the next adjacent node, node D. In the next line of code, we check, have we visited node D before? Yes, we have visited node D before. Therefore, we continue. And given that this is the last adjacent node of node E, the loop completes and the function call on node E completes as well, which means that node E has been completely explored and it leaves the call stack. So what this means is that we have finished with node E, which is the first adjacent node of node D. So we are taking up the second adjacent node of node D, which is node A. Now in node A, we check, have we visited this node A before? Yes, we have. So we continue and move to the next node. In the next node, we check again, have we visited this node before? Yes, we have visited this node before. So we continue. That means we go to the next node. Again, in the next node, we check, have we visited node C before? Yes, we have visited this node before. And because this is the last adjacent node of node D, the loop completes and the function call on node D also completes, which means that node D is now completely explored and therefore it leaves the call stack. This returns us back to the function call on node C. And given that node D is the last adjacent node of node C and we just finished processing the function call on this node, it means that we have equally finished processing the function call on node C. And so node C has been completely explored and then node C leaves the call stack. This brings us back to the function call on node B and we just completed the function call on the first adjacent node of node B, which is node C. So we take the next adjacent node of node B, which is node D. And now we check, have we visited node D before? Yes, we have visited node D and we have even explored node D. Therefore, we move to the next adjacent node of node B, which is node A. Again, we check, have we visited node A before? Yes, we have visited node A before, and node A is the last adjacent node of node B. So what this means is that the loop completes and the function call on node B equally completes. So node B is completely explored and it leaves the call stack. Then again, we are back to the function call on node A, and we just finished with the first adjacent node of node A, which is node B. So we are taking the next node, which is node D, and then we check, have we visited node D before? Yes, we have visited node D before and we have even explored node D. So we move to the next adjacent node of node A, which is node E. Now node E, we check, have we visited node E before? Yes, we have visited node E before and we have even explored node E. And node E is the last adjacent node of node A. So what this means is that the loop completes and the function call on node A equally completes. That means A is completely explored at this point and A equally leaves the call stack. So what this means is that we have finished traversing the graph. Now let's do a little recap. We started with node A, and in the recursive section of the function call on this node A, it's required that we will call this same function on all the adjacent nodes of node A, which is node B, node D, and node E. But we had to start with the first one, which is node B. So we call this function on node B. And then again, in the recursive section part of this function call on node B, we needed to call this function again on all the adjacent nodes of node B, which included node C, node D, and node A. We had to again start with the first adjacent node of node B, which is node C. So we call this function on node C, and again at the recursive section of this call, we needed to call this function again on all the adjacent nodes of node C, which are node B and node D. But then before we call this function on node B, our base case says that if a node has been visited before, just skip that node, continue, move to the next node. So now we are supposed to call this function on the first adjacent node of node C, which is node B. But because node B has been visited before, it skips it and goes to the next adjacent node, which is node D. And then calling this function on node D, in the recursive section of this function call on node D, we needed to also call this function again on all the adjacent nodes of node D. And we need to start with the first one, which is node E. Now, on the function call on node E, in the recursive section part, we also needed to call this function again on all the adjacent nodes of node E, which are node A and node D. But just before we call this function on each of these nodes, we find out that they have all been visited. So at this point, we have explored node E completely and we come back to node D. And then we finish exploring node D and then come back to node C, finish with node C, come back to node B, finish up with node B, and return back to node A. Okay, cool. So if you are new to graph data structure, this might not be easy to take in all at once, but don't worry. Take some time and soak it in. Rewatch the video if you must. Everything will make more sense once we begin to use all of this knowledge to solve top graph interview questions in the following videos. So go ahead and click the notification bell so you will get notified once I upload a new video. And finally, if this video was useful, please support my channel by subscribing to my channel. Also like this video and share with your friends. Thank you and bye.